When Robert Brown first observed pollen grains suspended in water, he noticed that they moved in a seemingly random way. This movement is what we now call Brownian motion. Later, Einstein provided an explanation by showing that this motion arises from countless collisions with water molecules. But how can we describe this motion mathematically? Since it's practically impossible to track every collision with every water molecule, we model it as a stochastic process. So for every point in time, we have a random variable which describes where the particle can be. We assume that the Brownian motion starts at the origin, that is, the probability that the particle is at position 0 at time 0 is 1. To understand Brownian motion, we can look at how the density behaves when many particles perform a Brownian motion. The density approximates the probability density function of the particle's position. As time passes, the particles spread out in a way that is similar to how heat spreads. In fact, the probability density function satisfies the heat equation, or in this context, the diffusion equation, where the constant d is the diffusion coefficient. Let's look again at the diffusion process, but this time at the density of the x-coordinates. The density of the x positions turns out to be approximately a normal distribution whose variance increases linear over time. In other words, the random variable representing the position of the Brownian motion is normally distributed with a variance that grows linear in time. This is consistent with the diffusion equation. The diffusion coefficient is half of the factor in the variance. This means that the increments starting at time 0 are normally distributed. But a Brownian motion is independent of the starting point, so we have that the increments at any point in time are normally distributed. Moreover, what happened in the past does not influence this increment, so we have that it is independent of all the past values. Another key observation is that the path traced by a Brownian motion is continuous. In formal terms, we require that the sample paths of the process are almost surely continuous, that is, with a probability of 1. All of these properties are encapsulated in the definition of a Wiener process. A Wiener process is a stochastic process that satisfies 4 essential properties. It starts at 0, has normally distributed independent increments with variance proportional to time, and its paths are almost surely continuous. In a Wiener process, the variance is normalized so that no additional scaling factor is needed. For example, this is a one-dimensional Wiener process. When we zoom in, we get another Wiener process. So a Wiener process is invariant under scaling. This self-similarity is similar to fractals. No matter how much you zoom in, the process looks statistically the same. This scale invariance implies that the particle, despite being observed over a finite time interval, follows a path of infinite length. To formalize this idea, we introduce the concept of total variation. Suppose you have a function, and the green dot travels according to this function. Then what is the distance traveled by the green dot? For that, we choose a partition of the domain. Then the sum of all the dashed lines is the distance traveled, which we call the total variation. More generally, the total variation of a function on an interval from a to b is defined by this formula. The supremum is taken over all possible partitions of the interval. For a continuously differentiable function, the total variation is simply the integral over the absolute value of its derivative. For a Wiener process, however, the total variation is infinite, so the path traveled by the particle in any finite amount of time would be infinite long. Instead of the total variation, we can use the quadratic variation to understand Wiener processes. Here we sum the square of differences and let the mesh of the partitions of the interval from 0 to t approach 0. For a Wiener process, we get that the quadratic variation is t. Another interesting property of Wiener processes is that the sample paths are almost surely nowhere differentiable. Although Wiener processes were first used to model Brownian motion in physics, a very important application is in finance, where we can model stock prices. Stock prices are influenced by countless unpredictable factors, similar to how the movement of pollen grains were influenced by countless water molecules. So we model the stock price by a stochastic process. Then at any point in time, the stock price changes proportional to its value. The randomness of these changes is modeled by a Wiener process. The sigma is a percentage volatility and models how much the stock price fluctuates. But right now we have not accounted for the fact that over time, general trends in the stock price can be visible, so we introduce a drift. This models how much the stock price grows or falls proportional to its value. What we have written down is a stochastic differential equation. A solution to this is called a geometric Brownian motion and can look like this.